Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into a fascinating Haskell implementation of an x86 assembler, leveraging the power of the Escardó-OlivaFunctional. It's a really clever approach, isn't it?
Absolutely. I'm particularly intrigued by how they tackle the challenge of x86 jump instructions. You know, the variable length of those jumps based on the offset, right? That's a real head-scratcher in assembler design.
Exactly. The problem is that you can't determine the size of a jump instruction until you know the distance to its target, but you don't know the distance until you've assembled the code between them. It's a classic chicken and egg situation. Classic!
So how does the Escardó-OlivaFunctional solve this circular dependency? I'm guessing it's not magic, but it sounds pretty close.
It's not magic, but it's elegant. The Escardó-OlivaFunctional frames the problem as a game. Each move is choosing the encoding, 2 or 5 bytes, for a jump instruction. The goal of the game is to minimize the total size of the assembled code. Clever, huh?
I see. So it's essentially finding the optimal strategy for encoding the jumps to minimize the overall size. But how does it actually find this optimal strategy?
That's where the selection functions come in. They're defined using a helper function called argent. This function iteratively explores possible encodings, discarding invalid ones, those that violate the -128 to 127 byte offset constraint for short jumps. It keeps track of the history of moves, ensuring consistency.
So it's a kind of search algorithm, but one that's cleverly integrated with the functional programming paradigm. Right? It's not a brute force search, is it?
No, it's not brute force. It's more of a sophisticated search, guided by the argent function and the constraints of the x86 instruction set. The beauty is that it's all expressed within the elegant framework of the Escardó-OlivaFunctional.
The article mentions using a bigatimes function. What's that all about?
Bigatimes is the core of the Escardó-OlivaFunctional. It takes a list of selection functions, one for each jump instruction, and a predicate that defines the outcome, total code size. It then uses these to compute the optimal sequence of moves, jump encodings, that minimize the outcome. It's a higher-order function that elegantly handles the dependencies between jump instructions.
So, the bigatimes function orchestrates the whole process, using the selection functions to explore possible encodings and the predicate to evaluate the outcome. Fascinating.
Precisely. The examples in the article demonstrate how changing the length of a loop in the assembly code affects the optimal encoding chosen by optimal play, highlighting the algorithm's ability to adapt to different code structures. It's quite remarkable.
I'm still trying to wrap my head around the J-monad mentioned in the code. Could you elaborate a bit on its role?
Sure. The J-monad, defined as type JRX equals x to r to x, is crucial for representing the selection functions. It allows the selection functions to access the history of moves and to return a move that depends on that history. It's a clever way to manage the state of the game as it progresses.
So it's not just about finding the optimal encoding, it's also about doing it in a way that's consistent and efficient, thanks to the monadic structure. Got it.
Exactly. The whole approach is a testament to the power of functional programming and its ability to elegantly solve complex problems. This Haskell implementation provides a clean and efficient solution to a problem that's often tackled with more cumbersome methods in other languages.
It's a really impressive demonstration of functional programming techniques. I'm definitely going to delve deeper into the code and try to understand it better. Thanks. Thanks for this insightful discussion.
My pleasure. And to our listeners, thank you for joining us on Tech Bytes and News. We hope you found this discussion as enlightening as we did. Until next time, goodbye.
Bye-bye.